Hey guys, very often I suggest that you should learn the basics of linear algebra for machine learning, and so I'm going to teach you those basics right now. So we're going to be defining a bunch of things. Firstly, I'm going to define a scalar. What is a scalar? And we've seen all of those before. It's really just a number, okay? Generally, that number is, we'll call it x in the reals, okay? So this is a general way to say it. We're saying some number x is a real number. So examples, well, we could have x equals 5. We could have, also y is equal to 7.2 or z equals negative 5.4. Those are all possible examples. They're all real numbers, which just means they range from negative infinity to infinity. And you can have like decimal numbers like this 5.4. You can have negatives. They are just numbers. One step up from that is a vector. Okay, so some people in physics might say a vector is something with a magnitude and a direction. I'm not going to call it that, although that is true. I'm just going to say a vector is an ordered sequence of numbers. So writing it generally, we would say something like x with an arrow above its head, so that means it's a vector, and then you'd say it's a member of the real numbers of n dimensions. So basically the n is how many numbers are in the sequence. That's an ordered sequence of 2, 3, 4 numbers, even one number, although that's really just a scalar. This you can imagine is kind of, there's an imaginary 1 up there, but we don't write that. So maybe, for example, you had a vector p. We can use a different letter for that. There's no reason. This is just the general way. We often use x, but you can also have a vector p, and maybe that was equal to, and I'll just keep consistent, for example, maybe we had p was equal to, 60 and 20. So maybe this is some sort of a person, and the first component, this piece is referring to maybe their height in centimeters. So I'll just say that's their height. And maybe the second piece is referring to their weight. So this is when we would use, say, a two-dimensional vector when we wanted to store information about two different aspects of some object. But you're not limited to 2 dimensions. Technically, p here, p was actually a member of the R2 family, meaning there's 2 different dimensions there. This is the first dimension. This is the second dimension, but we're not limited to that. We could also have, say, 3 dimensions. So you could have, I'll just call it z is equal to, 30, 20, and 10. And I'm not going to bother listing what these different components are, but this would be, if you wanted to store 3 different things about somebody, then that's how you would do it. And again, technically, z was a member of the R3 family because there's 3 dimensions. So you can graph some of these vectors or scalars. You could always graph a scalar because it would just be on a number line. For example, if we had this as a number line, maybe this was 0, and these were the negative numbers. So this is negative infinity way over here. And this is positive infinity over here. Maybe we'll just say that this is 100, for example, at negative 100. Well, if you had some point, maybe it was just the value of 3, well, then you could plot 3 right there. Although it's really not that interesting. We generally don't plot just scalars or one-dimensional things. We generally like plotting in 2 dimensions. So if you had then basically this same thing, but this is 1 dimension, if you did that 2 dimensions, you could put 1 horizontal, and that's generally what we refer to as the x-axis. Although in linear algebra, you might start to see this is the x1, and then this is the x2 axis. It's really just labeling dimensions. We're used to calling x the horizontal and used to calling y the vertical, but there's really no requirement to do that. But I will actually stick to the x and y axes because I think it's easier to understand. So maybe if you had a vector which would say, and it's weird, but I'm going to call it x as well. Don't get that confused with this x over here. That's just the axis. This is actually the vector. So maybe we had x is a 2-dimensional vector, which is 3 and then 4. Well, we could plot that as this as well. This is the x-axis and this is the y-axis. X is 3 and y is 4. So maybe we'd plot that as maybe 3 is over here on the x-axis, and then 4 is up here on the y-axis. We would draw the intersection of those things, and we'd plot that vector right at that piece there. Okay, so now I'm going to move on to specific operations that you can perform on these vectors. Very, very analogous to, we know that 5 plus 5 is equal to 12. No, I'm just kidding. It's equal to 10. And we know that, say, 10 minus 4 is equal to 6. we know that 4 divided by 2 is equal to 2. We know that there's also the modulo operator, although we don't use that quite as commonly. We know 3 modulus 2 actually means taking the remainder, which happens to be 1. We can do very similar things. I'm actually not going to do this one. We can do very similar things with vectors, and that can be very useful. So for example, you can multiply a scalar by a vector. To show you this, I am going to start writing vectors generally as x is equal to, we'll write x1, x2, down until xn, and that is implying that x is actually a member of the Rn family. So this is just saying, like, we have dot 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 because we don't know how big the dimension is. We're keeping it generic, and so the dimension is n. So n is at least 1, generally bigger than 1, so at least 2. You can think of it probably as at least 2. So if we did multiply a scalar by a vector, that would be s, so some scalar, I'll write it s in the reals, that's just some number, and then some vector, we'll write x in Rn. So if we combine these things, if we did s times x, well, that is simply equal to, well, if x is this thing right here, that is equal to s times x1, s times x2, down until s times xn. So for example, maybe we did sx, where s is equal to 4, and x is we'll say it's a 2-dimensional vector, so that's setting x equal to 2 here. There's 2 components in the vector. If we had x equal to maybe 2 and then 4, well, we could do sx, which is actually equal to, replace that with 4, replace that with 2 and 4, and then that goes into each component. So that goes 4 times 2, I'll write it like this, we'll see why later, 4 times 2, and then 4 times 4, which is just, well, we know how to do that. It is just 8 and then 16. So all that's saying, if you multiply some number times a vector, that means all of those components that we have, we mean these things, it's individual numbers as components. It means that we multiply each of those components by the scalar. Very similarly, we can also add vectors, as long as they're the same dimension, because if you did try to do something like 3, 2, and then you tried to add that with 4, 5, 6, we would be like, well, what are you talking about? This doesn't line up. I mean, maybe you could have done something like this is equal to, 3 and 4 is 7, 2 and 5 is also 7, and then I guess 6 and 0, but technically in linear algebra, this is undefined. So this doesn't actually exist. We would never do something like this. What you can do is add vectors of the same dimension. So it kind of makes sense if you had, 3, 2, and then you were adding, 4 and 5. Well, that is equal to the sum of the components. So that is 3 plus 4, and this is 2 plus 5, which is equal to, when we know how to do that, that is 7 and then 7, and it's also a 2-dimensional vector. So if you're adding vectors in a given dimension, so this one is 2, if you're adding vectors in 2 dimensions, you're going to get 2 dimensions back. Similarly, but really is identically the same thing, you could also do subtraction. So if we did 3, 2, and then minus 4, and then 5, well, technically what that is just addition. It's 3, 2, you could replace that with plus the negative 4 and negative 5, and we know how to do that. That is 3 and negative 4 makes negative 1, and 2 and negative 5 makes negative 3. Exactly the same thing as addition, but with negative numbers. So basically the dot product, if you had 2 vectors, we'll say A is equal to 4, 3, and then we had another vector, B is equal to 10, and then 12. If you did A and then the dot product, A dot B, that's why I was using that cross as multiplication to not be confused with the dot product here, A dot B. So this is equal to, we get the first component of A, which is 4. I'm actually now just going to write multiplication as putting brackets beside each other like this. So 4 and then 10. So that's this component times that component. We take those two and then we add that to this component 3 times this component over here with B, 12. Okay, so we take each of the matching components. We have these things here, 4 and 10. I'm just going to erase the B, and even though it actually is B, I'll just put that over there. So we have 4 and 10 match up, and 3 and 12 match up. So 4 and 10 match up, 3 and 12 match up, and we multiply those pieces. And then with the whole vector dot product, we actually end up summing those multiplications. So 4 times 10 plus 3 times 12, that is equal to 40 plus 36, and that is equal to 76. Okay, so we use the dot product for many reasons, and that will come up soon. For now, I'm going to introduce this new thing, the transpose operation. So if we had x as some vector, maybe it's 4 and then 2. Well, if we had x transpose, so x, we write it with a t over here, x transpose, that is equal to actually just a reorganization. It is 4 and then 2 like this. Now I'm going to ignore that transpose for now. It might not seem very useful. It's like we just shifted horizontally. Well, I'll show you shortly why we might want to do that. So now we'll introduce something called a matrix, or if you had multiple of them, it would be matrices. We would write it generally similar to the vector, but it's more complicated. X is a member of the real numbers where it's m by n. Okay, we write that up at the top saying there's basically two axes now. So the x is a vector in Rn. Well, that was referring to just going down like this, x1, x2, until we hit xn. But there's no reason you can't have multiple axes to make what's basically a table of information. So we're going to make that now, and in linear algebra, we call it a matrix. So if you were to do this generically, it would be this big table where the first component is x. Well, it's the first row. So a row refers to, this is the first row, this is the second row, and a column. So this first column, this is the second column. So the first row, so x1 and then 1. The first number refers to the row, the second number refers to the column. So it's x1, 1. If we went down a row, what happens? Well, the first number refers to the row, so this increased. So this will be x2, 1, because the column stayed the same. And it goes all the way down until, well, look what's increasing. This went from 1 to 2, and it goes all the way down. It would help if I wrote m over here and n over here. This will be going down until there's m rows, and it's still in the first column. If we moved over one column, it would be x, and then, well, the second column, but the row stayed the same, so still the first row, but then the second column. And then if we go down 1 like that, so the row increased, this will be x2, but the column stayed the same, so x2, 2. That goes all the way down until x, well, it's going to be m still, but in the second column. Now if we go all the way across, we actually have, well, all in the first row, so it's still x1, but then it goes until x1n. And over here, well, it's the second row, so it's still x2, but now it's x2n, the last column. Then we generally write it like this, just dots all leading up until the last component, where that has to be the final row and the final column. There is m rows and there is n columns, so it's xmn in the corner. So just an example, maybe we had some matrix, which is really just a table of information. Maybe we had x as a member of the 3 by 2 family. That means it has 3 rows and 2 columns. We had that maybe equal to maybe 1, 2, 3, and then there's 2 columns, so it'd just be maybe 4, 5, 6. This is perfectly valid. There's 3 rows, 1, 2, 3, and there is 2 columns, so 1, 2 columns like that. Now you definitely might be wondering why suddenly we made n, like n was going vertically here for when it was a vector, and so that would kind of make sense for it to go until this is n rows, except I actually did m rows, and then n got stuck in the sideways, in the horizontal format here. I'll show you that very shortly, but for now I'll show you that we can actually write a matrix. Okay, sorry, I just copy pasted that x over here, so this is actually the same x. X is in the reals of m by n. So we could actually rewrite this if we wanted to, as if we treated each row, for example, as a vector. You might as well. A vector is a sequence of numbers, so the row is all staying the same, and so it's just a sequence of numbers in a row, but it has n pieces, 1, 2, up until n. Well, we can take advantage of that, and so we could simply write this as, well, this would be x1, because, this 1 is staying the same, x1, and then transpose. So if we made that a vector, where it just has n components, that's x1 transpose. And same thing over here for these pieces over here. Well, we could easily write that as x2 transpose. And so this goes all the way down until, well, it's the mth row or the last row, and then transpose. It's transpose because that's how it was writing horizontally like that. If we didn't have the transpose, that would then kind of picture them all crumbling down like this. That wouldn't make much sense. It goes horizontal, and so it kind of fills out like that. So now I can define matrix vector multiplication, the multiplication between a matrix and a vector. If we had maybe one matrix, we'll call it X is an R M by N. And if we had a vector, I'll use a different letter. A is in the reals of N. It has to be of dimension N, and I'll show you why shortly. Sorry for the crazy jump where I just changed headphones. Sorry about that. We can do something called matrix vector multiplication, where we have a matrix on the left and a vector on the right. So that looks, again, I'll just copy this off screen. That is X, the matrix, and then you write the vector A, A1, A2, up until an over here, utilizing the transpose and the dot product. This is just x1 transpose, as we saw, x2 transpose, and then xm transpose. We've already seen that, so that's nothing new. And then I'm just going to write that vector again, a1, a2, up until an. And I'll show you in a second, we actually don't even need to have a written out like this. We can just have x1 transpose, x2 transpose, up until xm transpose. Again, nothing changed there at all. And then I'm just going to put a back here, like it was at the beginning, because what this is all actually equal to is simply x1 transpose dot a, and then x2 transpose dot a, and then all the way until xm transpose dot a. We just take that vector A and we do the dot product with every single row. And so that's going to leave a vector with m dimensions, because each of these things, this is a bunch of multiplications and then a summation. Each of these things is actually only one number. This produces a number, this produces a number, and this produces a number. And so it's just m different numbers now. It made an m dimensional vector, and all of this very complicated thing, that just bottles down to taking this vector here. So whatever we have over here, we take that vector and then we dot product with this row here. And then after that, we take that vector and we dot product with that row there. And we do that every single time, the exact same vector. We dot product that with every single row to produce an m-dimensional vector. That's it. What it technically is without any sort of math hiding it with any symbols. So if we turn the dot product into what it actually means, it's x1 times a1 plus x1, so I'm keeping that same number because this is for each row. So x1, 2 times a2 plus dot 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 until how many columns do we have? Well, it's going to be still first row, but then n columns. So x1, n, and then I'm just going to do without the brackets, an, like that. And then the second row, x2, 1 times a1. It's the same a1 plus x2, 2 times a2. It's still a2, and then plus all the way until x, it's still the second row, and then there's n columns, and then again an, like that. We do that all the way down until we have m rows, so xm1 times a1 plus xm2 times a2 plus dot 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 plus xmn times an. And again, there should be brackets around this an. It just means multiplication with that particular unit, so I'll try to put that in there. Basically, again, no matter how you want to say it, you take the vector on the right, and then you dot product it with each individual row. And we do this in many different applications in machine learning. So say, for example, we had some matrix X, and we set that equal to maybe 1, 2, 3, 4, 5, and 6. And then we had some vector A. So A is equal to, well, it has to have 2 dimensions. We have to be able to dot product it with that horizontal. So it has to be something like maybe 3 and then 10. So if we did the matrix vector multiplication, which is the matrix on the left, and the vector on the right, which is replaced with what they actually are, 1, 2, 3, 4, 5, 6, and then the vector, which is 3, and then 10, we would do the dot product. And so this 3, 10 would dot product with 1, 2. So that will be 3 times 1 plus 2 times 10. And then the second row will be the same vector here, dot product with that row. And so it's 3 and then 3 plus 4 and then 10. And then our final row is 310 dot product with 5, 6. So it's 3 and 5 plus 6 and 10. And we can do that math. That is simply equal to, well, one intermediate step. It's 3 plus 20, 9 plus 40. That's a 9. 15 plus 60, which is finally equal to that addition. 23, 49, 75 is our final vector for the matrix vector multiplication of that matrix and that vector. So a good practice is to go to a matrix vector multiplication website, put in this matrix and that vector, and make sure you get the same results. And I'm going to leave it at that. The next logical step is to do something called matrix-matrix multiplication, maybe eigenvalue decomposition, and matrix inverses. But honestly, to get going, this is mostly what you need. You're not going to go too much more complex into the strict linear algebra side most of the time, but I will probably proceed this series. So if there is more linear algebra stuff, check the link in the description below. And if there is a video at that time, then you can proceed to watch the next one. Thanks so much for watching this one. Drop a like if it helped you out, and I'll see you in the next one, guys.